So now that we've established a type of reference electrode, let's look at it, using it to do an electrochemical measurement. So we'll have our same setup here, where we have again our saturated KCl solution, so KCl here on the bottom, our silver solid with silver chloride on the outside of it, and this is, we have a salt bridge. And this is connected to a platinum wire. There's a potentiometer here. And this is connected to a platinum wire. And we have a mixture of iron 2 plus and iron 3 plus in solution. So how can we use this to find out something about this iron 2 plus and iron 3 plus? Since there are two things there, we actually have two unknowns, so we can't find the concentration of just one of these, but we can find the ratio of the concentrations. If we look at the inertia equation for this right-hand cell on our positive side, let's say that we have positive and negative here. So this reaction is going to be the reduction of iron 3 to iron 2. This has a known standard potential of 0.771 volts. If we write the Nernst equation for the positive side, we'll get E naught positive side, which E naught we have right above, minus 0.05916 volts divided by 1, because there's only one electron. And then we'll have the log of concentration of iron 2 plus divided by the concentration of iron 3 plus. So our one unknown thing that we have here is this ratio here. And this is the information we can get from our cell. If we measure the overall potential of the cell, we'll know that, right? That'll be a measurement that we make. The left-hand side, the negative terminal, we know the potential of that because it is a reference electrode that has a fixed potential because of the fixed concentration of chloride. And so then on the right-hand side, the only thing we don't know is this ratio. So if we measure the potential for the overall galvanic cell, we can figure out the ratio of the concentrations of iron 2 and iron 3. So let's look at that. Let's imagine that we measured 0.5 volts as the potential for the whole cell. So let's write out an equation to allow us to determine this unknown ratio of iron 2 plus and iron 3 plus. So we'd have 0.5 volts. This is our E total. Is going to be equal to that's our wrong one. We're going to have 0.771. I had our potentials backwards. 0.771 volts minus 0.05916 over 1 volt times log of x. We'll call this ratio here x. All right, and so just to keep track of what all these are, this is E naught for the positive terminal for that iron 3 reduction, and then the extra terms here from the Nernst equation. And then we'll subtract, right, so overall this is just E plus. And then we'll subtract E minus, which we know is 0.197 volts. So that is not the standard potential, but that is the actual potential, right? So the potential compared to hydrogen for the silver chloride reference electrode. So we can see X here. This is our one unknown. We can go ahead and solve this equation. All right, and once we do, we'll know the ratio of these concentrations. All right, so we need to subtract this term and this term over to the other side of the equation. Well, I guess subtract and add. So we'll get negative 0.074 volts is equal to negative 0.05916 volts times the log of x. And then we can go ahead and finish the algebra here. So we'll get that the log of x is equal to 1.251. So x will be equal 10 to the 1.251, which gives us 17.8. So what that means is because we measured a voltage of 0.5 volts on this overall cell, we know that the ratio of our iron species is 17.8, meaning there's 17.8 times more iron 2 than iron 3. Maybe this is a way that we want to monitor reduction happening in the cell or something like that. and this would give us a way to keep track of what's going on with these different ratios. So this is an example of how we can use this to do a analytical measurement. We got some information about the concentrations of species in this system. So in the next video, we'll look at how we can package this reference electrode, right? Instead of needing a whole beaker, sort of as we've drawn it, we can do this in a much smaller package. We'll look at that in the next video, as well as another commonly used reference electrode.